In the first half of this lesson, we talked about how to take a function and write it as a power series representation. So we start off now learning what operations can we do once we have these functions written as power series. The first of which tells us that we are allowed to evaluate that function at a constant multiple of x. And that's simply just going to replace x in the power series with kx. So now kx is raised to the nth power. We still have this coefficient of a sub n, but now k has an exponent of n as well as x has an exponent of n. We are also allowed to evaluate these power series at different powers of n. So again, I'm just going into the power series and I am replacing the x with x to the capital N. And we do know from rules of exponents that that tells us that we should multiply these exponents. And then finally, we are allowed to add or subtract those two power series. We would do that by adding or subtracting respectively, depending on what operations we used between the functions, the coefficients that show up in that power series. So we're going to be able to use this to take power series that we already have and build new power series by either adding power series together or replacing x from old power series with maybe x squared in new power series, and we'll see examples of that worked out. It is important to note, though, that when you add two power series, which we're about to do an example for, it is possible that you're changing your interval of convergence. So, for example, looking at these two power series here, we know that this first power series will converge when the absolute value of x is less than 1, which means that x needs to be on the interval from -1 to 1, and the second power series will converge when the absolute value of x over 2 is less than 1, which means that x needs to be on the interval from -2 to 2. So we have two power series and two different intervals of convergence. Let's see what happens when we add them. So adding them, I just need to add x to the n with x over 2 to the n. Let's do a little bit of algebra. So we have x to the n added with x to the n divided by 2 to the n. X to the n is common among both terms, so I'm going to factor that out. I'm going to factor it out in the back so it will look like a power series. So what does that leave me with? It leaves me with a 1 plus 1 over 2 to the n. This is a new power series now. When will this power series converge? Notice that factoring out that x to the n was very helpful because now I can see this is only going, well, even without factoring that out, if the first sum only converged between -1 and 1 and the second sum only converged between -2 and 2, then the sum of those sums is going to converge where they both converge. So it's going to only converge on the interval from -1 to 1. Point being that when you take two power series and you add them, the resultant power series is convergent on the intersection of those two original series. So taking where they both originally converged, that will tell you where your new series will converge. In example 4, we want to find a power series representation for this rational function. First thing I'm going to do is observe that my denominator is not linear. It does not look like 1 minus r, which is huge for us because the whole way that we do these problems is we consider the fact that a geometric sum converges to a over 1 minus r. The absolute value of r is less than 1. So we're trying to get our function to look like this, which is not going to happen if we have x squared minus 1 in the denominator. So the first thing we need to do is decompose this into partial fractions. The denominator factors into x plus 1, x minus 1, and we should be able to eventually find, I'm not going to go through the algebra of this, that a is 2 and that b is 1. So now we do have this decomposed into partial fractions. I'm going to rearrange the way I write these. I'm going to write these as so they look more like this, because now the idea is that we have this function and this function with linear denominators that we should be able to match to that form. So I'm going to reorder the denominator. I'm going to write this as 1 plus x in the first term and as negative x plus 1 in the second term. So the first term is pretty much just about set up. I can see that a is going to be 2 and that r is going to be a negative x. In the second term, I need this to be a positive 1 in order to match it to that form. So I'm going to have to come in and divide all of these terms by negative 1. So now I have a negative 1 divided by 1 minus x. So now I can see in the second term that a is negative 1 and that r is simply a positive x. So now we should be able to write these as power series. In the first one, we have the sum from n equals 0 to infinity of a, which in this case is 2, r to the n. R in this case is a negative x. In the second sum, we have the sum from n equals 0 to infinity of a, which in this case is negative 1. R to the n, in this case r is x. The first sum will converge when the absolute value of r, which is absolute value of x, is less than 1. Second sum will converge when the absolute value of x is less than 1. So good, they have the same interval of convergence, so the overall sum is just going to converge when the absolute value of x is less than 1 on the interval from negative 1 to 1. And the last thing I'll do is I'll just clean this up. Because I can write this all as one sum now rather than two separate ones. So we have 2 negative x to the n plus, or really just a minus, because this is just a negative x to the n right here. And in that first term of the sum, because of the negative x to the n, it's truly alternating. So I'm just going to pull out the negative 1 to the n. I'll leave the x to the n there. And the last thing I'll do is I will factor out the x to the n, because now both terms have the x to the n in them. You've seen me do this before. I'm going to factor it out on the back end so it looks like a power series. Leaves me with 2, negative 1 to the n in the first term, and a minus 1 in the second term. And now we have a power series representation for our function. And it did require us to decompose into partial fractions and to go through finding a power series representation for each one of those functions individually. And then once we had those power series representations, we could combine them inside the sum and do some algebra to simplify. And I will add on here at the end, just because it's a part of my answer, what that interval for convergence is, which if we actually solved would be negative 1 to 1. So in example 5, we want to find a power series for the function f of x is equal to natural log of x, which may seem a little odd at first, because for all of the problems that we've been doing so far, we have very specifically been using the fact that we know that a geometric sum of the form ar to the n converges to a divided by 1 minus r if the absolute value of r is less than 1. So what we have been doing is we have been taking our functions, which have always been rational functions, and retrofitting them to this. But obviously, natural log of x is not rational. So we're going to have to use a different approach to be able to retrofit our function to a rational function to be able to form a power series. And how we're going to do that is using this information that's written above that tells us that a power series behaves like a polynomial. within its interval of convergence. What does that mean? That means that we're able to take derivatives and integrals term by term of a power series without changing the radius of convergence. So how does that help us? Well, the function f of x is equal to natural log of x, which is not rational, but its derivative, f prime of x, is equal to 1 over x. So essentially what we want to do in this problem is we want a power series for 1 over x. And then once we have that power series, how we're going to get back to natural log of x is we're going to integrate that power series term by term. So we've already written a power series for f prime of x. I'm just going to rewrite this so I have space to write next to it. We wrote a power series for 1 over x back in example 3. We have this representation here on an interval of convergence from 0 to 2, open on both endpoints. I'm going to add that in here. Because the power series doesn't mean anything unless you also discuss where it converges. So we have a representation for f prime of x, which now what I'm going to do to both sides of this equation is I'm going to integrate. And when I say both sides, I have the arrow from f prime, but I'm really integrating 1 over x. The integral of 1 over x dx must be equal to the integral of this power series. And I am adding dx on the end of both integrals. The integral of 1 over x is natural log x. That's exactly why we chose it. I'm not putting the plus c on that side because I am going to put the plus c over here. And I don't need to write it on both sides of the equation. Let's look carefully at what we're being asked to do right here. We're being asked to integrate a sum, right? A sum is just a list of terms. So if I'm integrating a sum, basically I am integrating all of these terms individually, and then I'm adding them all up. So I can switch the order of the integral and the sum. Instead of integrating the sum, I can say, oh, we'll take the sum of all of the integrals. And now let's look at this expression inside here that we're integrating. All of this right here is a constant. So as we integrate that, nothing is going to change. Integrating x minus 1 to the n power, we're going to have to increase our exponent by 1. Even if we're just doing a u sub, lucky for us, u is x minus 1. du is simply dx, so we don't have to go through a substitution. Make sure you divide by your new exponent, and we already have our constant of integration added on at the end. So we have this expression for natural log of x that has this plus c on it. So it's not quite a power series yet, not with this undetermined coefficient of plus c there. Let's try to figure out if we can solve for c. If we're saying this is true, remember we have an interval of convergence from 0 to 2. So we can't use any x values that are outside of 0 or 2. Hopefully you would think, I would hope you would think that x equal to 1 is a good x value to use to solve for c. Because if I let x equal to 1, immediately on the left side of the equation, natural log of 1 is equal to 0. And then on the right side of the equation, if x is 1, this whole x minus 1 factor is going to go to 0. So I'm left with 0 is equal to c. So now we have a full representation for the power, a full power series representation for natural log of x, that it's equal to the sum from 0 to infinity of negative 1 to the n, x minus 1 to the n plus 1, all divided by n plus 1. Now, in terms of its interval of convergence, we knew that 0, 2 was the interval of convergence for 1 over x. This is going back from example 2. We had found an interval of convergence from 0 to 2 open on both endpoints. However, we are allowed to take derivatives and integrals term by term in power series, but the endpoints of the interval may behave differently. So I don't necessarily know that this interval, that this power series converges from 0 to 2. It could converge on 0, 2. It may converge on 0, 2 closed on both ends. It may close on 0 and open on 2. It may converge on open on 0 and closed on 2. But one of these four will be correct, simply because I knew that this was the interval of convergence for the function that we took the integral of in order to get this one. The correct interval of convergence is the latter one, and you should be able to work through that using what you learned last week about power series. You should be able to take this power series and find its interval of convergence, open on 0 and closed on 2. And really, all you're doing is you're testing what happens when x is equal to 0, and you're testing what happens when x is equal to 2. And it looks like in both cases you'd just be working with, well, no you wouldn't. But you should be able to test those series and see what's happening to determine convergence at those endpoints. In example 6, we're being asked to find a power series representation for f of x equal to arctan of x centered at 0. So again, notice that this function, similar to the last function, is not rational, so we're going to have to be using some kind of differentiation or integration to be able to even use a power series here, because the whole way that we do these is that we retrofit rational functions of the form a over 1 minus r, considering the absolute value of r less than 1, and we turn them into power series. So using what we know, I'm going to just differentiate f of x. We know the derivative of arctangent is 1 over 1 plus x squared. So hopefully we'll be able to use that, because now we do have a rational function. However, it's a little problematic for us that this rational function is quadratic in the denominator. So I'm going to instead consider a new function, g of x, that's no longer quadratic in the denominator. I'm just going to make it linear in the denominator. So I definitely do know how to form a power series for this function. If it's helpful, you can write this as 1 over 1 minus negative x. So you can clearly see that a is 1 and that r is negative x for the power series for g of x. So before I even fill that out, I want to discuss, why does this help us? Why am I able to just drop the exponent down to something linear? Well, remember, we know how to form this power series. So it's not going to be an issue for us to fill this out for that there. Now, the difference in the exponents here, we'll be able to compensate for that because in the properties that we saw here above on operations with series, we saw that if we have a power series representation for some function f of x, we can form a new power series by plugging in a different power of x. So if I'm able to form a power series representation for 1 over 1 plus x, if that's my function f of x, and I'm able to form a power series for that, then I can form a power series for a new function by plugging in x to the n, in my case x squared, and I'll go into the power series and replace that x with x squared, the same way we saw in those properties. So that's how these properties are going to help us build power series for functions. So going back down, let's go ahead and finish writing this power series. So filling my pieces in, I have the sum from n equals 0 to infinity of a, which in this case is 1, which I don't need to write, r, which is negative x, raised to the n power. I will clean that up a little bit. This is just a negative 1 to the n, x to the n, and this converges only when the absolute value of r is less than 1. In this case, r is negative x, so its absolute value is just x, which has to be less than 1. So we have an interval of convergence from negative 1 to 1 for this power series for 1 over 1 plus x. Now, let's substitute x squared for x. So now we have g of x squared. So I'm now going into where x was in g, and I'm replacing that x with x squared. Composition, this is going back to 171. So now I'm going to go into the power series, and I'm going to replace this x with x squared. So this now becomes the series from n equals 0 to infinity of negative 1 to the n, x squared to the n, which is now the sum from n equals 0 to infinity. We still have the negative 1 to the n, and x is now raised to the 2n power. So now we have a representation for 1 over x squared. I'm just going to write that very clearly. We have a power series representation for 1 over 1 plus x squared. That's not what I said the first time. So now that we have this power series representation, I'm going to come in and I'm going to integrate both sides. And the whole reason that we're integrating both sides is because we know that the integral of 1 over 1 plus x squared is arctan x. You won't see me write the plus c on the left side because I will write the plus c on the right side. I'm going to be integrating the right side of this equation as well. Integrating a sum is the same thing as taking the sum of many integrals. So I'm switching the order of the sum and the integration. I'm integrating negative 1 to the n, which is just a constant, x to the 2n dx. So now I'm going to be increasing my exponent by 1. I still have my sum, but now I'm actually applying the integral, so that's gone. My constant of negative 1 to the n is going to stay the same. I've increased my exponent by 1. It's now 2n plus 1. And I need to divide by my new exponent. Once I've integrated, I need to add my plus c. We need to figure out what the value of c is. Keep in mind that our interval of convergence was negative 1 to 1, so we cannot be using x values outside of the interval from negative 1 to 1. I do know what the value of arctangent is at, say, 0, and 0 is a good x value to plug in because of this term right here. Let's let x equal 0. So we get arctan of 0 equals, well, that entire sum just goes to 0, plus c. And arctangent of 0 is 0, because 0 is the only angle between negative pi over 2 and pi over 2 that has a tangent value of 0. So now we know that c is equal to 0, and we are done. We have arctangent x with a power series representation of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all divided by 2n converge. As for the interval of convergence of this series, it's going to be one of these four. This was the first one that we had from the series of for 1 plus 1 over x. You would then need to test the endpoints, same way we did back when we learned about power series, and you should be able to conclude that the correct interval of convergence is negative 1 excluded, but positive 1 included.